elements are objects in the lower stages of the hierarchy at no point do we encounter a set that contains itself. Do you see the thing here? Since we are creating more and more complicated sets in this fashion, and at any stage of the hierarchy, if you consider a set, then its objects are, its elements are objects from the lower stages of the hierarchy. So you can never have the set containing itself because it's in the same level of the hierarchy, which is only being formed using lower objects of lower status in the hierarchy. So that's how we can avoid having a set containing itself. However, this is a rather complicated process, and to formalize this actually, mathematically or logically, it turns out to be very difficult. To formalize the above discussion or approach, however, turns out to be rather difficult, because you have to precisely say what the stages of the hierarchy are, then you have to define each rank of the hierarchy precisely, and it's an involved process. Instead, we will introduce a new axiom which will ensure that absurdities such as Russell's paradox do not occur. Okay, instead of following this approach, we are going to introduce a new axiom which will eventually show us, it will be a consequence of that axiom, that Russell's paradox does not, things like that do not occur. So here is a new axiom. Axiom, this is 9. It also has a name, regularity. This is known as the axiom of regularity, and it says this: if A is a non-empty set, if A is a non-empty set, then it has at least one element X such that either X is not a set, that means either X is a primitive object, or X is a set and is disjoint with A. Okay, either X is not a set, or if it is a set, then it is disjoint with A. It has no intersection with A. Now, this axiom looks rather strange, and it's not at all, it's not that natural. It does not have the naturality of the previous axioms that we have seen so far. However, let us just see what this axiom is and what its consequences are. This axiom is also known as the Axiom of Foundation. It asserts that any non-empty set has an element which is so low in the hierarchy of objects that it does not contain any other element of any non-empty set. Let us just call it A, since we are saying it A. Any other element of A. So that sort of object X we are talking about here in this axiom, which is so low in the hierarchy of objects that it does not contain any element of A. Because you see, when we form A, what do we use as its elements? The objects which are in the previous rung, the lower rung in the hierarchy. However, there will be at least one object which is so low in this hierarchy of objects that it cannot contain any element of A. Okay, if that makes sense. An example will be more clear, will make it more clear. For instance, take A to be this set, say 3, 4. Okay, I should carefully write this. 4. Okay. Have a look at this set. Oh, yes, I made a mistake. It's not a mistake, but this is the set actually. Okay, so note carefully that A contains 2 elements. Both of them are sets. In A, the element is a set and is disjoint with A. Because 3 and 4 are not elements of A. The elements of A are both sets. Note that 3 and 4 are not elements of A. So this is an object, this set, in a lower rank, at the lower stages of the hierarchy of objects. However, the other element, what about this element? The element being this element that we are considering now, this other set, this is somewhat higher in the hierarchy of objects, definitely higher than this one, because this is a primitive set. It has only primitive objects as elements. This, however, is not a primitive set, because its elements are primitive objects and a primitive set. Okay, being somewhat higher in the hierarchy of objects contains an element of A, namely this. So simply because the elements in the first element are so low in the hierarchy of things that they cannot be elements in the original set A. That's why this element is disjoint with the empty set. The axiom we have introduced right now, regularity, assures us that any non-empty set has at least one such element, which is the lowest in the hierarchy of objects. But because we have not defined hierarchy or any such sort of structure formally, we are resorting to an axiom. Okay. Now, one consequence of this axiom of regularity is that sets are no longer allowed to contain themselves, and this is the second exercise. Okay, so this is our new axiom, but now a question arises. One can legitimately ask whether we need the axiom of regularity in analysis, since it is certainly less intuitive than the other axioms. It is certainly less intuitive than the other axioms we have seen so far. And the answer is no. Okay. It turns out that to actually do analysis, we never need this axiom. And what is the reason for that? The reason is that in analysis, the sets we consider are very low in the hierarchy of objects, in that actual hierarchy. Because the sets we consider in analysis are very low in the hierarchy of objects. Do I have any ink left? If not, then I have to open a new bottle, or I think I can use this one, the other one. If I have something to finish this hierarchy of objects, being sets of primitive objects or sets of primitive objects or at worst, in the worst case, sets of primitive objects. I can give you an example. If you are familiar with topology, at one point we will study that. Then there we consider, of course, every now and then in mathematics, in the very easy parts of mathematics also, we consider sets of primitive objects. They are just ordinary sets where the elements are primitive objects. Sets of primitive objects. An example of that is a topology. Or we need not go in fact to topology. We can consider the power set of a set whose objects are themselves primitive sets, that is sets of primitive objects. And if you consider a collection of power sets of some set, or for example power set of a power set, then that is a set of primitive objects. More than this, we do not need to go to any higher rung in the hierarchy of set theory. Okay, so that's why we don't really need this axiom, the axiom of regularity or the axiom of foundation. However, one needs the Axiom of Foundation to perform more advanced set theory. But we have chosen it to include just for the sake of completeness, and also to see how one can get rid of Russell's paradox. Okay, that thing is still there. We have to look at that in the exercises. But that's why this has been kept in an optional section. But for us, nothing is optional. We are going to see everything. So the next thing is the exercises.